business card.
This lady said that you.
Where's mine? Where's mine?
Oh, these are your business cards?
Yeah.
These will be okay. Yes, ma'am.
Recording.
Not yet. I'll get signed.
Yeah. It said go, that's why I asked.
Oh,
This is the chapter that we were working on. Everybody okay with these symbols for the limit switch? Are there any questions on limit switch? We run these things. When's the last time you ran into a limit switch? Today? Where did you run to it today?
Opening the door of the car.
Open the door of the car, that switch in there that does that is a limit switch. You know, the light on the refrigerator uses a limit switch. These are mechanical switches, right? You understand. Y'all seen them before. So that's what's turning your light off and on your car, when you get in and out of the door. So normally, the one in your car, which one would be the symbol in your car?
It will be normally closed.
Well, it's not normally closed, because if it was normally closed, your lights in your car would be on all the time. What's that? This one? Okay, so is your doors normally open, or is your doors normally closed? Okay, so this is the one right here. So you have a normally open, right? You'll understand, I'm sorry. Normally closed. What? Where's it at? You have this right here. A normally closed, tail open. Y'all understand?
When you open the door, it breaks.
Yeah. So it's a normally closed, which means when the plunger's out, the contact's closed. Right? You'll understand. But your door is normally closed, right? You'll understand that. So we have a what in our car? We have a normally closed, tail open. Y'all understand that? Yes or no? That's a real good example. This is what they're showing here, basically what we're talking about. All electrical circuits, including the source, load, control devices, and conductors. Most circuits also include a what? Some type of overcurrent protection device. So the minimum requirements for a circuit is a voltage source, a load, and conductors, right? But normally, what does a circuit have? Normally, a circuit has some type of control device, right? At least one. The names of this course is motor control. So we're going to be dealing with a lot of control devices. You know, when does the motor stop? When does the motor run? How do we reverse it? How do we make them sequence start? How do we make them automatic reverse after a certain amount of time? And also, most circuits is going to have some type of protection on them. Overcurrent protection devices, and we looked at two different types. We talked about fuses, and we talked about circuit breakers. Are we okay there? So we have two types of diagram at the top. What's the top one? The top one is a ladder, right, or line. This is a pictorial. Y'all understand the difference? We've added a new feature up to the top. First of all, this is not true for ours. Ours is ungrounded. So we notice we have this symbol right up here. What's this a symbol for? A device called a transformer. And what does a transformer do for us?
Step up, step down.
The voltage plus the current, right? Most people say the voltage, but if you change the voltage, you change the current, right? You understand that? Why doesn't it change? Yeah, I know. We don't step up or step down power. That's the trick.
Oh, it keeps trying to.
Yeah, say don't try. It does a really good job in it. So it means if I need 100 watts over here, what are we gonna get over here? We're gonna get 100 watts. But that's gonna be at a different voltage. You'll understand.
Current and voltage go in different directions.
Yeah, so in a transformer, the current and the voltage goes in the different directions. And this gets people confused because people say, well, if you raise the voltage to the load, then the current go up. But we're not talking about we're not talking about the load, we're talking about the source, right? You understand? We're talking about the source of that current. What sets the current? What sets the power in the current? Well, the load sets the power in the current. It's just that when you run a load, you're going to run it at a certain, don't think resistors, think about motors and stuff like that. Those things are designed to run at a certain voltage and produce a certain power at a certain voltage. If you don't give it the right voltage, then it's not going to produce the right power, right? You'll understand that. So loads are designed, most loads except resistors. What are resistors rated in, by the way? Okay, they're rated in ohms. What else are they rated in? You're going to be in trouble. It's just like when you're going to go out here to a tire place and say, I need some tires. What you got? I don't know. What you going to buy? I don't know. Right? What is, yeah, that's what they're rated in. I mean, you can't just go out. If you go online and you look for a 100 ohm resistor, you're going to find a lot of stuff that goes along. There's a lot of stuff that goes along with a 100 ohm resistor. It's just like I'm saying, you go down here and say, I need to buy a tire. What are they going to what they want? What are they going to ask? Right? Well, what size tire do you need? So you go out there, you go down, you can buy a tire down here at Walmart for your lawnmower, but that, by George, it's not going to fit on your car, but it's still called a what? It's still called a tire. So when you go out and you buy tires, and if you got a lawnmower and you need a tire, you just can't go in and say, well, I need a tire, because they're going to give you the wrong size, almost totally guaranteed, right? You understand that? So we got to get that information off the side of the tire that gives us the aspect ratio and the rim size and all that other kind of stuff. Okay. So what else is it rated in? What'd you say, Charles? Wattage. Yeah. If you don't know the wattage of a resistor, then you don't need to go out and buy a resistor. We were teaching a power supply class, and I've told some of my class know this, and they needed a 100 ohm resistor. And they just looked in their kit and they found a 100 ohm resistor, and they stuck it in there. And they kept coming up there and saying, well, Rich, something's wrong with my power supply. It keeps burning up these resistors. Well, what was the problem? Well, yeah, they was putting, this is a 100 ohm resistor, and we was putting 30 volts on that thing. So that's going to be 30 squared divided by 100, right? You understand? So that's going to be what? What's 30 squared? 900 divided by 100. So they needed a 9 watt resistor, and they was putting a 1/4 watt resistor in there and burning them up as fast as they put them in there. And they was trying to bring the power supply, but all they was looking for is a watt. All they was looking for is a 100 ohm resistor. What's the third thing it's rated in? It's not rated in a voltage. So over in our solid state class, we're learning how to do basic design of regulated power supplies. And that's what you got to understand. You know, you calculate the size of a resistor. You just can't say I'm going to round up or going to round down. It depends on which way the tolerance is going to go, right? You understand that? So these are the 3 things that a resistors are rated in. Rated in ohms, rated in watts, rated in what? Tolerance. And if you don't know those 3 things right there, then you don't need to buy what you want. You don't need to go buy a resistor. You're either going to buy a resistor that's got a higher wattage rate than you need, and they occupy a lot of board space, right? You understand it costs a lot of money. So it's your ultimate goal. Just about any business you're in, your ultimate goal is to make money.
So if you needed one with a real tight tolerance, you go 5% instead of the 10.
Well, no, we got better percentages than that. So normally what we got is what we call a 4-band resistor. It's number, multiplier, tolerance, right? You understand? We have 5-band resistors, which is number, multiplier, tolerance. These guys are gonna have like a brown band on. What do y'all think brown would mean? 1%. Red would mean 2%. So we have 1% resistors we can buy. We got 2%. We got purple. We got different tolerances, but the stricter the tolerance it is, the more it's going to cost, right? You understand? So normally here we teach 4-band resistors, but 5-band resistors are out there. I think they introduced those to you in the intro, right? 5-band resistors. So yeah, we got different tolerances between the 10. The 20, which you don't hardly see anymore, the 20 didn't have a tolerance band. So we said the 20%, we called it a neutral color or transparent. And then we have silver, which is what? 10%. Then we have gold, which is 5%. And that's the predominant percentage. But you will run into 5-band resistors. And their tolerance bands are pretty close to what we're going to deal with. Brown would be 1%. Red would be 2%, and I would have to look at some of the other ones. So when we buy loads, so there's one thing that's not included in resistors, and that's the voltage. And then the current's not in there either. So you can run different voltages at different currents as long as you don't exceed the what? The wattage rate. Now transformers, and most of your loads, like your motors and your light bulbs and your chargers and all this kind of stuff that you plug into these wall outlets, is going to have a voltage rating. Y'all understand that? And if you don't give that device the right voltage rating, then you're going to have problems. It's going to give you a voltage rating at a certain current, or it's going to give you a voltage rating at a certain wattage. So what advantage does high voltage have? Well, high voltage means I can provide more watts at a lower current. Right, you understand? Or the same watts at a lower current would probably be more correct. And then what advantage does low voltage have? Well, it's safer. What advantage does DC have? Well, DC, we can electronically control DC. We cannot electronically control AC. So if I'm going to electronically control AC, then I convert it to DC, and then I can use DC to regenerate an AC, right? You understand? But now the AC that I'm regenerating, I'm doing what? I'm controlling it, right? You understand that? So that's the big advantage of AC, is that we can step it up and step it down. Plus, it induces the voltage in the motor, so we have what we call induction motors, which one of the magnets is actually induced. So this transformer up here, this is what we call a dual. Most companies, just like your house, most companies have multiple voltages. If they're high wattage devices, they're going to buy those for high voltage, and then your low wattage devices, they're going to run those on a lower voltage, right? You understand that? So we have different transformers that we have most of your transformers are what they call multi-voltage or we're using what we call a dual voltage transformer. So notice up here on the primary side, we've got these jumpers up here that we jump depending on what we want to do. Our ultimate goal is to get 120 volts right there. Because all our relays are rated at 120 volts. All our light bulbs are rated at 120 volts. So everything we hook over on this side is going to be rated at what? 120 volts. If I put 240 volts on them, what's going to happen? Well, they're going to all burn up. Because power, if we double the voltage, power goes up by 4, right? If we put 60 volts on it, then they will do 1/4 of the work. Everybody okay? And we'll see that. We're going to deliberately do some stuff in this class just to let you see things, stuff that we would not do in real life on purpose. I can't say you'd never do it. Knuckleheads get out there and do wrong things all the time. So what we have on this, so if I wire DC power sources in series, we got 2 ways we can hook up these power sources. Actually, we got multiple ways, but the 2 most predominant ways is what we can hook them up in parallel or we can hook up in series. Normally when we hook them up in series, we hook them up in what we call series 80, power sources. Now what do we get when we hook sources in series 80? Add them, but what do we add? So let's say this guy right here is rated at 10 milliamps and this guy right here is rated at 20 milliamps. Now this is 5 volts and this is 6 volts. What do we add? We add both, okay. So that means across here I would get 11 volts at what current? No way, right? This guy right here can only put out 10, it cannot put out 30. This guy right here can only put out 20, it cannot put out 30. So the best we can do out of this is 10 milliamps. Series circuit current is the same through everything in the circuit. So here it would be your worst case. Whichever battery had the worst case, that's what the circuit would be rated at. So what you get is you add the voltage together. Okay, y'all understand? Yes or no? So we can use different batteries. Normally all your AA batteries and AAA batteries are going to be rated the same. But you get some higher power batteries. Well, you're not going to get that extra current if you're going to run another battery in there that can't give you that, right? You understand that? Okay, so what do we get right here? First of all, we can't use different size batteries down here. They have to be the same size. And let's say this guy here is rated at 10 milliamps and this battery right here is rated at 20 milliamps. And what do we get when we hook them in a parallel like this? What voltage will we get? No, they're not going to cancel. They're pointing in the same direction. Negative to negative, positive to positive. We get 5 volts out. And what would our current be? It's going to be 30 milliamps. So in parallel, the current's at. So if I hook batteries in parallel or cells in parallel, we increase the current carrying capabilities of the batteries, but we don't increase the voltage. If we hook them in series, we do what? We increase the voltage, but do what? Okay. So over here, we're going to deal with turn ratio. So I can hook those. So right now we have these coils up there hooked in series. Can y'all see? So here comes the transformer. And this would be 2 of our power lines. 3-phase, what you need to do if you're in a 3-phase system, what they do is they stagger the transformers between like L1, L2, then they go L2, L3, then they go L1, L3. It don't make any difference, but they don't put all their transformers on one phase. Their ultimate goal is to balance the phases. It's just like at your house. When you put circuit breakers in your panel box, what should you do? You should go from side to side, side to side, side to side. You shouldn't load up one side and then move over to the other. Because if you do that, you're going to put all your 120 volt loads over on one side of your transformer. Right? You understand that? So you need to stagger the loads. Or even the single phase loads. Everybody follow me so far? Have I lost anybody? Huh? Okay. So we got this transformer right here that we got. By the way, the way industrial transformers are labeled is we have 2 sides. We have a high side and we have a low side. So when we color this in and we don't color it in, it means it's what we call a terminal or a connection too, right? You understand? And then over here we've got the secondary on our transformer. It's not a tapped. Now what they do is this goes H1, this goes H2, this goes H3, this goes H4, and then this right over here, this goes X1 and X2. So the secondary, the low voltage side, so X is for the what? we have the low voltage. And the H's make sense. The H's are for the what? High voltage. So we can make it step up or we can make it step down. So if I use this for my primary and this for my secondary, then we can step up. If I use this for my primary and this for my secondary, then we can step down. Y'all understand the primary and the secondary terms? So the primary is the windings of the transformers that's pointing back toward the original source. And then the secondaries are the side that's pointing toward the load. So if we run into Alabama Power, we'd probably have a transformer here, then we'd go over here, then we might have another set of transformers here, then we'd go to here, and then we might have another set of transformers here, right? You understand that? Well, all these on this side, every one of them that's pointing back toward the source would be the what? So this would be the primary, this would be the primary, this would be the primary, this would be the secondary. I'm sorry. Which one's pointing back toward the source? So this would be the primary, this would be the secondary, this would be the primary, this would be the secondary. Okay, y'all understand that? So how we're gonna wire this up, guys? So what we're shooting for in our class is we're shooting for 120 volts right here. And our transformer can either be connected to 240. Up here we can either connect to 240 or 220. Or, I'm sorry, 240 or 440. Or 460. I don't remember. I have to go look. We'll see how this works out. Okay. So how would I hook them up if I want to get 120 volts right here and I'm putting 440 up here? We'll just use 440. That works out better. 480. I'll get this right here. Well, our transformer is it's a 4-to-1 or it's a 2-to-1. So we can wire this up here to get a 4-to-1, or we can wire it up to be. Would you think? Who would think that? Well, what you got to understand, always, we wire H1 and H2 back to the line. So these guys right here go back to L. One of them might be L1, the other one might be L2. One of them might be, or it might be L2 to L3, or it might be L3, L1 to L3. So H1 and H4 go back to power. So all we're going to do is somehow we're going to wire up the transformer. Now we got two options. We can either wire those coils in series or we can wire them in parallel. Now if I wire them in parallel, when I wire stuff in parallel, we keep a voltage, but we change the current, right? You understand? Okay. If we wire them in series, we keep the same current, change the voltage. So what we're trying to do is wire it for 440. So I want to divide by what? I want to divide by 4. So what do we want? Do we want a lower turn ratio over here, or do we want a higher turn ratio over here?
What was the point there?
Up here on there. We don't rewire the secondary.
I see your mark not showing up.
What do you mean?
Okay, now.
The primary or the what? We're not going to rewire the secondary. We're trying to get the same voltage out of the secondary, whether we have 480 or whether we have 240. That's what we're trying to do. And we got two options on the primary. We can either wire it for what we call low volt. We can wire it for a what? A divide by 4, or we can wire it for a divide by 2.
Okay, divide by 4.
Yeah, because we're going from 480. We're trying to go from 480 down to what? 120.
divide by 2. H2.
Divide by 4.
We're not gonna divide by 2 because 480 divided by 2 is what? 240. We done screwed the pooch, right? So understand, we done burn our everything up. So we're gonna do what? We wanna figure out how to divide 480 by 4, which is gonna give us what? 120. Everybody okay? That makes sense? So we're gonna divide by 4.
So Jackson, how to wire that up to make it 120?
We have to wire the primary up to give us 120. So how are we gonna connect those?
H2,
Like H1 to X4, H4 to X2.
If we take H1 to X1, we just blew up everything.
Oh, yeah, you don't,
Because your primary and your secondary are
you don't want.
we never, ever, unless we run a ground, by the way, is connect the H's to the X's. This is the output of the transformer. This is the input of the transformer.
Where does it come out?
It comes out right here. This is where our power is going to go out to our circuits down here.
I was on power on one end, your house. on the
Can you
other.
pull one off the middle?
It's over the house.
What's that?
Over the house or something like that.
Yeah.
Hold to the house.
No, this is right up here. So I'll give y'all, let me call this. So I would come up here and I would connect H2 to H3. Now what I've done is I increased the voltage we can put across of it, and if the voltage goes up in the power source, the current goes down. Now, we don't have 480. We got, what did I say? We can use what we got over there, but it don't really make any difference. So what we got up here is we got about 210. We got about 210 up here. So we're not going to quite get 120. But let's use 240. Okay. So what do I want to do down here? Well, I don't want to wire them in series. I want to wire them in what? Parallel. So how would I wire them in parallel? So here comes my power, H1, H3. So these are going to be my lines coming in for my 3-phase. I'm going to tie H3 to H1 and tie H2 to H4. Now look, what I just did is I did what? Cross wires. So what they did a long time ago, so you can check this out really, really fast, is they deliberately, on the diagram, cross these wires right here. So what they do, and this is the way the transformer's wired. So if you look at the actual lugs on the transformer, it went H1, and then the next was what? H3, and the next one was what? H2, and then H4. And I'll show you why they did it like that. So in actuality, the transformer, when they bring it out to the terminals, what they do is they come over here and cross these two right here. Not to make it confusion, to make it easier for us to wire. So this would be H1, this would be what? This would be H3, right? This would be H2, and this would be H4. So if I want to wire it for high voltage, then I would come over here and I'd put my jumper right there. No crossing wires, right? You understand. If I wanted to wire it for low voltage, which is what we're going to do. Well, by the way, you'll wire it both ways. When you do your transformer lab. If I wire, then this one would jump to that one, and this one would jump to that one, and I have no crossing wires. So what happens when you buy your transformer, you get these two little jumper plug things that look like this. So it'll come over here, it'll have a little slot right there, and then it'll have a gap, and it'll have a little slot right there, and this will be a jumping plug. So what that means is you get two of them. So that means, and these are screws right here, right? You understand that? So what I can do, if I want to wire them for high voltage, I just take this little old jumper and do what? Put it right there, and I put the other one right there, and I'm ready to go. So that's why they deliberately do what? They deliberately cross what? H3 and H2 on the terminal board, so we can use these little jumper plugs that you can stick down there. And you can jump them real fast. But all I gotta do is go up there and look, and if I see crossing wires on the top of that transformer, I know what? I know it's wired wrong. So this one is right. So right now, if you go up there, you'd see a jumper between H1 and H3, and you'd see a jumper between H2 and H4. And then, of course, H1 and H2 is going to go back over to two of the lines. And y'all need to stagger those, right? We know hook them up. So some of y'all need to use what? L1, L2, and we'll figure out how we go down there. The next group needs to probably use what? L2, L3. The other one needs to do L1, L3, and then we'll start the sequence over. Because what we need to try to do is do what? Balance the load on our three-phase panel box out in the hall. So this is what we've got. And then of course what's going to come over here is that this is going to be our fuse. We don't have the fuse. By the way, this is the international symbol for a fuse. And then over here, this is what we're going to call L1, and over here we're going to call this L2. We're going to give it a little. We're going to give it a little bit of a name. We're going to call it CL1 and CL2, because what we got up here is we got an L1 and an L2 up here, and then we're calling this L1 and L2 down there, and they are not the same. One of them's three-phase, one of them's single-phase. Right? You understand? For control line, for control L1 and control L2. So this is where we're going to come down here, and we'll connect our control circuits down here, our ladder lock. And so we have a terminal right there, and we have a terminal right there, and every one of our devices has terminals. Are you okay? So that's what they're showing us. Oops, I was at the right place I wanted to be at. As soon as I get over to the right one. So this one right here is wired for, this right here is wired for high voltage.
Yeah.
So they're putting 115 volts up there. If that's a divided by 4, what would we be getting on the primary? You know, secondary? Huh? What would we get? Huh? What would we be getting?
28.75. 28.75.
Yeah, so probably up at 24 volt control. But this is pretty much all the same. But ours, though, we're not grounded. We're not going to use grounded on the other side. When you go through a transformer, you lose you're transferring that power magnetically, not electrically. So as soon as you go through a transformer, if the primary is grounded, the secondary is ungrounded. Y'all understand that? Ungrounded sometimes is a little safer in this situation because we don't have a lot of metal in this class. At home, ungrounded would not be good. So we got everything except this little guy right here. And what's the difference on ours? Over here we got a watt. And then we got a fuse. So this is a pictorial and a ladder diagram. L1, L2. By the way, we have 3 categories of relays. So the smallest category we're going to refer to as a control relay. And then after that, we have what we call a contactor. And then after that, we have what we call a motor starter. Legally, this should be called a magnetic motor starter. Because I feel magnetic. Okay. So this circuit right here probably works out. We just have to run power, but I'm gonna have to get it off and know what we got. This is a control relay. So a control relay is a relay whose contacts, y'all understand those terms now. So a relay is, we'll call this guy right here, this is not actually a motor. We'll call this guy right here, this is the symbol of a coil. Y'all understand that term now? Yes or no? Yes or no? Everybody okay with that?
We're getting it now.
So the coil is the portion of the relay that creates the magnetic field. Right? You understand? We call these guys here contacts. And we would call this a normally open contact. Everybody understand that? Let me get a little better diagram. Where's it at? So there's that's a wiring diagram. This is a schematic. And then this right here would be a ladder diagram. Now this is without the transformer, without the power. All our diagrams will start off with the power source. Normally on a ladder diagram, they take for granted the power source is there. But since we have to wire the transformer, they're going to show the transformer. Okay, so this little circle right here, this is our symbol for what? Coil. Relay coil. Now notice on this side, so basically the layout of a diagram. You start off with L1. We're going to trace it from left to right. We start off with L1. And what's the first thing we're probably going to run into? We're going to run into our control section. How are we going to control this? These guys can be series, they can be parallel, they can be series parallel, and it does not determine what type of circuit this is. This is a single load series circuit, right? You understand that? Everybody okay there? Yes or no? Okay. So notice here we start off basically the same. So this right here is our watt. This right here is our control. And then this right here is our watt. This is our load. So in this one, this guy right here is the load. Everybody okay? Now, this is kind of different. There will only be one type of relay that has these contacts on the right-hand side. That means this guy right here is going to be a magnetic motor starter. So the main function of this relay is to start and stop a what? Motor. Now the problem with motors, so you're sitting out there in your car and you're at a red light and you want to start moving. What do you start doing? Well, you don't just touch your gas pedal. You have to push your gas pedal down a pretty good deal, right? You understand? And then you get your car going. And then what do you start doing? Easing off. So anything that's at rest wants to stay at rest. Anything that's in motion wants to stay in motion, right? You understand? So that means when we start a motor pulls a lot of current. We call it the starting current. Starting current, rule of thumb, generically, of course, we'll look at later on when we get into trying to read the nameplate of a motor. There's a code on there that you can look up that gives you a multiplier for the starting current. So when you look at the nameplate of a motor, it's going to say amps. Well, that amp is run current. That is not start current. That is run current. Rule of thumb is start current is 6 to 8 times the run current. If you don't have the data, then that's what we use. So it means I got this motor out here. Now the motor's not in here, so we'll run into two sections. So out here we might have a motor, a 3-phase motor, by the way. And let's say this thing's rated at 10 amps. Right? You understand that? Which would be a pretty good deal of horsepower, isn't it? So how much would it pull when we tried to start it? This would be the run current. How much would it pull generically? How much would it pull when we tried to start it? Up to 60, might be up to 60 to 80 amps. Now, if we stall it, what's it gonna pull? It's gonna pull 60 to 80 amps if you accidentally stall the motor. So what would my overcurrent protection device that's protecting that motor, would it trip at 10 amps or would it trip at 80 amps? 80. You have to, the motor's got to start. If we put a fuse at 10 amps, right, you understand, every time you tried to start the motor, if the motor was up and running, it'd be okay. Right, you understand. But if we tried to start this motor, it would blow the fuse. So we would have to fuse the line at 80 amps. Well, what would happen if the motor stalled? It'd burn up. Right, because now it's going to try to pull starting current. If it stalls, it's going to try to start, right? You understand that? So it pulls starting current, and we don't have any protection for it, so it would burn up. So what we have to do on motors is we have to have a secondary protection. We call them overloads. So this is the motor starter, and I just bring the camera out. I'll bring it up. No, I can't. I'll have to get my camera. Fortunately, this guy don't support the camera. So this is a magnetic motor starter. Now this is the actual relay right here. But we see something down below it. These are called overloads. Now what overloads allow to happen is it allows you to have overcurrent over time. Y'all understand that? So that means if you pull too much current, these guys here don't trip instantly. So they will let the motor do what? They'll let the motor start. And then if something happens, if the motor don't start, or if the motor stalls, then over a set amount of time, this right here will kick the circuit out. Now, what are we going to kick out? Well, we're going to kick out the relay that's controlling the motor, right? Y'all understand what we're saying? Yeah, so these are overloads down here at the bottom. This is a magnetic motor starter. So, normally what we do, normally what we do is 90% of the time we never have anything between the load and L2. The only thing that's allowed in between L2 and the relay coil is these things called what? Overloads. So that means this will start the motor. Over here we'll have contacts over here. They're going to be labeled M. So I hit this button right here. This relay comes in. This closes. The motor starts. This over here is okay, right? You understand? Okay. Something happens, the motor stalls or the motor don't start. After a little while, it's going to do what? It's going to kick out one of these guys. And then it's going to kill the motor starter, the relay, which is going to open these contacts over here, right? You understand that? So the only thing allowed between L1, the only thing allowed between the motor and L2 is what? Overload contact. So you can tell right off the bat if the relay is a motor starter, because if it's a magnetic motor starter, it will have overloads. Everybody understand that? Yes or no? Okay, guys, I'll go ahead and take a 2-minute break. This is what we call a motor starter. Okay, and a motor starter is designed to run what? Motors that don't have internal overloads. Now, a lot of your single-phase motors have overloads built in them. They're built in them. Sometimes they'll have a little red button on them that you can push. Sometimes they auto reset. So that means that you try to overload them, the little thermal overload will kick out, and after it cools back on, it's going to do take off, especially in all your HVA systems, guys. So be real careful there, because that can eat you up. Our overloads our motors are what we call dual voltage motors, so we can wire them either way. And since the voltage is not set, because if you run the motor on low voltage, it's going to pull more current to develop that horsepower, right? You understand? If you run it on a higher voltage, it's going to be less current to produce that horsepower. course, it costs the same thing. Y'all understand that? That's what gets people confused. Because you're not paying for voltage, you're not paying for current, you're paying for watts. So if I have something that's designed for high voltage, if I put it on that high voltage, it will mean it's going to be cheaper to run because it's going to be 1800 watts at that voltage, right? You understand that? What it means is I can use smaller conductors to get that power out. So these are the overloads right here. I'm sorry, these are the overloads right here. These are what we call thermal overloads. Some motor starters have electronic overloads in them. These are probably the ones you'll run in most often because these are so much cheaper. New applications, you'll probably use electronic overloads. Older applications, they'll probably use what we call thermal overloads. And then we have, these are what we call manufacturer numbers, which we'll look at later on, that tells us how to connect up this motor starter. This is the reset button right here for your overloads. So if your overloads trip, they are tripped. It's just like a circuit breaker in your house. But those suckers don't reset automatically, do they? So this is where we'd reset the overloads right here. Now this has contacts on it. But then on the side, it's got, so these are our power contacts right here. So these would run the motor. And then over here on this side, we have what we call auxiliary contacts. So auxiliary contacts stay inside the control circuit. Your power contacts are outside the control circuit. Y'all understand that? So normally what we have is we have two circuits associated with a control diagram, which we'll eventually get to. We'll have a control circuit, and then we will have a power circuit. The control circuit is usually going to be low voltage, right? So this is our control circuit where you're looking over here. But this runs a motor. Well, what was the motor? This is not the motor. This is what? That's the coil for the relay. Well, where's the motor at? Well, the motor is going to be over here somewhere in a power circuit using the power contacts. Okay, and this is a symbol for a three-phase motor. And now this is M. This is M. This is labeled M. This is labeled M. These over here are going to be called what? M. These right here is going to be going to L1, L2, and L3, which is three-phase. So when I press this button right here, what's going to happen? It's going to let current flow through here. It's going to hit the coil. This is already made up. We don't have an overload. Then it's going to do what? It's going to seal itself in. Now I can do what with the push button? Let it go. Now as soon as this right here makes, this over here is going to close, which is going to cause the what? Motor run. But the motor's not in, the motor circuit is not in the control. The contacts don't show you in the control circuit. It's going to be in the what? The power circuit. Now, but what would happen if the motor started pulling too much current? One of its overloads you're going to trip. It'll open that contact, cause this thing right here to do what? De-energize or drop out. And now we can't start it until we do what? Until we clear up the overload. Everybody okay? Pretty neat. So these, when I look at these diagrams, this guy here has three power contacts for three-phase. They call them, I don't know if y'all can see right here, L1, L2, L3. And then this right here would be an auxiliary contact, and this right here would be an auxiliary contact. Auxiliary contacts are contacts that stay inside the control circuit, and then your power contacts are what's actually running the what? The load, the main load. So on this diagram right here, these two right here would be auxiliary contacts because they are inside the control circuit, right? That makes sense? Now this is a relay called a contactor. This is a high current relay, but it does not have overload. See, up here it's still got the watts. Up here it's still got the L1, L2, L3. And down here on the load side, they're labeled what? T1, T2, T3. But if I look on the side, these are auxiliary contacts. So these auxiliary contacts are the contacts that stay in the control circuit, and then the power contacts will be in the power circuit, right? You'll understand that. Most of your controls are set up like that. So this has two sets of by the way, your relays, most of your relays have what we call, the books refer to this as push to test. I've never really, this is the first time I've ever heard that. We call this a mechanical override. We call this an override. So what I'm doing is I'm simulating the coil. Can you see this guy here at move? So what it's doing is these set of contacts are made, and then of course all these contacts are made. Your new relays, by the way, you're not going to see the contacts. The contacts, and we'll talk about later, are going to be inside of chutes. They're going to be sealed up. You can still maintain them, but we'd have to remove this cover to see the contacts, because we don't want to expose to the air something's going to be arcing and sparking and stuff like that when it makes and breaks, right? And then we isolate the power contacts from each other, and we'll talk about that later. So a contactor is a relay that's designed to run in both the control circuit and the power circuit, but it doesn't have overloads. So either the motor you're going to run has overloads built into it, or it's going to run some other power device that don't require overloads. You'll understand that. So what are the overloads in there for? Well, it allows us, and my camera stopped working, it allows us to fuse the circuit at the start current and still protect the motor, because your fuses have to let the start current get through, right? You understand that? All these others, this is a ladder diagram came from US Steel, and this is the control circuit. Are some of these motor starters? Well, it don't look like none of them motor starters because there's no loss. Well, there's no overload. Yeah, these are contactors. They're not motor starters. They're contactors. Because a lot of these are running from Sure Enough Motors. If you look at the nomenclature over here, I'll give you all a copy of these sooner or later. I don't need to remind you that. So number 5, bridle reverse relay. Well, this is going to cause the motor to reverse. Well, if it's going to cause the motor to reverse, and by George, it's got to be controlling the motor, right? You understand that? So most of these in this are actually contactors. They're not. I don't know if there's any control relays in here. They're called an L1 and L2, PCL1 and PCL2. These guys, by the way, ran DC motors. And we looked at one-line diagrams. Let's see, where was we at? Limit switches, we okay. I went back to my blank page is what I did. And all these now are just circuits, right? They show us a pictorial. They show us the ladder. Now, which one would be easier to troubleshoot with? Well, the ladder diagram's easy for me because it shows you the logic of the circuit. This down here at the bottom don't really show me anything because it's full of pictures. But if I was a novice and didn't understand it, I would like the pictures because now I can go and look at the parts, right? You understand? Over time, you know what these parts look like. That would be like you carrying a picture of your car, trying to figure out where your car is parked at. Right? You understand? Well, you might have to do it for a little while, especially if you go from one car to a new car. You ever did that? Yeah. And then come out and can't find it because why?
Like somebody stole it.
Well, you're looking for your other car. And then you realize, dang, we bought a new car. Float switches. So here we're using a float switch. Y'all understand float switches? So y'all supposed to start memorizing these symbols. We told y'all where there's at, right? There's going to be a lot of them on the test today. If you didn't say those symbols, you're in trouble. Solenoids, everybody okay on the solenoid? What's this guy over here called? It's called a plunger. Technically, we refer to it as the armature. I need to get over here and do this. I have a bad habit. So this guy right here is armature, and it's just a what? It's just a. So we put power on the coil. What happens? It causes this guy to move. It's just as simple as that. And what do we do to get a relay? We just attach that armature to what? To contact. So this would be a contactor, not a control relay. Control relays are going to be real small little things. A control relay, all the contacts of a control relay stay in the control circuit. That's why they're called what? Control relays. So here's a perfect example right here. So I have a ladder diagram at the top, L1, L2, then we have a pictorial. So this is our ladder diagram. This is our power circuit right here. And it's usually drawn as a what? Wiring diagram. So here we got a relay called C. Here, by the way, this is the, I don't know if y'all books got this corrected or not, but here they're calling the relay what? C1. Over here they're calling it what? Yeah, these contacts have to have exactly the same name as the relay itself. Yeah, they never did correct that. This is, by the way, in the book, if you're following the book, we're over on page, the new book, we're on page 51. The old book, I would have to figure out what page that's on, guys. I'm sorry. It's in the chapter on symbols. So auxiliary contacts may be added to contactors or motor starters to run inside the control circuit, is what y'all need to see. Right? You understand that? So auxiliary contacts of a contactor are usually in the control circuit, and then your power contacts are going to be out where? In the power circuit. Y'all understand the difference between those two? So most control diagrams, most motor control diagrams consist of two diagrams. It's going to consist of the control diagram and then the what? The power diagram. The power diagram will be a wiring diagram, and it's going to include everything. But normally we're not concerned with the everything. What we're concerned with is this guy right here. Here's our power. So this is a single phase motor, right? You okay? Yes or no? Now this is a motor starter. So what's the difference between a contactor and a motor starter? This don't test, guys. What's the difference between a contactor and a motor starter? Just got it out. Just got it. Just got through talking about both of those. Motor starter has. My motor starter has overloads. Period. A contactor does not. Y'all understand that? A motor starter has overloads. A contactor does not. Does it mean a contactor is not going to run a motor? No. It just means it would run a motor that don't need overloads. So a lot of your single voltage motors, the overloads are built into the motor. It's required. So all motors above, things like it's 1 horsepower, have to be overload protected. They have to be overloaded. If it stalls or if it don't start, yeah. Or if it takes too long to start. And so your house does not have motor starters in it. It's got contactors. So if you went out there and looked at your HVA system, those overloads are built into the motor. We need to do a lab here pretty soon. I'm fixing to stop. Let's see. Let me find. This is a stator of a 3-speed motor. It's very common in HVAC systems. So the brown wires are for the start capacitor, guys. Oh, I don't know if my camera's going to work. It locked up on me a while ago. I think I exited it out. Let's see. But I can't show y'all this, but when you look at this, when I pass it around, you'll be able to see it. But these are, we call this the stator windings right here. And then you see 2 red wires come out of it. And there's a little old metal thing right there. This is the overload inside this motor. So this guy here would not require an external overload because why? The overload is built inside of it. Who's turning? That's a 3-speed, single-phase, fast skip start motor. And the 2 big brown wires coming out there is for the start capacitor. We talked a little bit about that, right? Huh? Goes on the blower. Goes on the blower. Most, just about all, every external HVAC system I've seen for years uses a 3-speed motor.
Well, that overall reset itself.
Yeah, that's a thermal overload. It resets itself. A lot of times those things will go out because they're outside, you know, and they're exposed a lot. And that's all that's wrong with the motor is the overload goes out in it. If the overload goes out, it's not going to run. It's not going to start.
Right. We get to keep these, though.
Yeah, these are y'all's. And these are our lab procedures for the class. And we have to go by the lab procedures, guys. Y'all understand that? So you need to look at this, and we go over it in class. Some of y'all have had my classes before. You just have to live with them. Some of y'all hadn't had my classes. So when we start dealing with, you know, voltages and current plus how smooth the class runs, we need to follow procedures, right? You understand that? So everybody should have got one. This has got everything about the lab. The first thing we're going to look at is the actual procedures for the lab. And what's the first thing it says up there?
Safety glasses must be worn.
Yeah, anytime when you're over at the lab station, right? Short pants or open-toed shoes, footwear are not allowed. Orthopedic clothing is not allowed when working in the lab. We've already talked about this, right? Leather palm gloves. Of course, if you get leather gloves, that's fine. Must be worn when doing what? Making energized circuits measurements. Do not make any connections or circuit modifications while circuit is engaged. Does that make sense? A short circuit test must be made on each circuit before applying power. We'll do that with an ohm meter. Live voltage test must be performed before making circuit connections or modifications. A lot of people take for granted when you click a disconnect or something like that, that power is removed. Now, 99.9% of the time, that's a good assumption, but it's that 1% that's going to get you, right? You understand? So anytime you do a disconnect or anything like that, what do you need to do before you put your hands in the circuit? You need to get your voltmeter out and make sure the circuit does not have, because disconnects are made with contacts. Contacts stick together, right? You understand that? Our disconnect is a relay control disconnect. Knife switches are probably a little better because most of the time when you well, even with knife switches, you might run into problems. Verify that both connections are made to the transformer after each short circuit test. So what happened?
This paper is ETC 120. It's a little different than what you got.
Oh, it is?
Yeah.
I ran off the wrong ones. Yeah.
I was wondering, I could look it up today.
I thought he powerful.
Y'all look at these. I'll run these off before you. I'll run these off and make sure y'all get them. If you're an ETC 120, you can keep it. Most of this, but I need to run this. I really need to run this off before y'all leave. I'll run it off to the printer down there because y'all got a quiz on this. If you ever worked in the trade, you understand that the more conductors you put under a terminal, the more likelihood it's going to come loose. Okay. If you ever worked in the trade and you ever looked at your power, you'll notice that your transformers only have 2 wires going through. Because everything else is junk, right? You understand that? So what we do is here is we have no more than 2 conductors are allowed under any terminal. First of all, ours, we're using banana plugs. Y'all see how this guy's hooked up here? So we're using what we call banana plug jumpers. All you're depending on, if you ever looked at a banana plug, the actual male connector, it just has metal out and it expands out, and when you push it in, so the only thing it's holding on to is the side. So you start stringing them things out the bottom, right? You understand what's going to happen to the road. You're going to pull out, right? Some of our banana plug jumpers have covers on them. So if they do pop out, they automatically cover themselves up. Now those things are really, really nice. But if you put those things on the bottom terminal, they're going to come out all the time. So if you're going to use those things, you need to make sure you only use them on the wall, on the top. No more than 2 of those plugs under any terminal. So when we look at and I can't get my camera working, guys. Let me try this. I see a camera up here. Logitech, there it is up there. It says it's not responding. Yeah, it locked up while I was using it. Locked up. So when we look at these terminals, why these trainers have lasted so long is we don't allow the students to screw and unscrew screws. We used to scrap things all the time. We used to actually have to wire it up. So this is before we got the motor control trainers we have now. Those big panels back there is what we use. The big gray panels back there on that thing. And the way they had to hook them up to is everything was hooked up to terminal boards. And for some reason, people don't understand how to use terminal boards. They either strip the screws out, right? You understand? Usually what happens, they strip the screws out. So what we decided to do was go to another technique where we go ahead and put like what we call banana plugs under the I know it's not responding. It won't let me. It won't even let me. And then what we do is we attach what we call banana plug jumpers. And if you look at these things, you'll notice we have a male, and then each male has a female on the back of it. So what that means is we can come up here and stack these things together like this, right? Y'all understand that?
You calling it, or what were you calling banana?
These are called banana plugs. That's their
Never
name.
heard of it.
Really?
Yeah, I'm lost.
The same thing that's on your meter, because they covered up.
Yeah, the new meters are covered up. Banana plugs have been around, jumpers have been around for years. And what it does is it allows us to make temporary connections real fast, right? Like your meters were soldered in, and old meters used to be like that. Then first of all, when you damage your banana plugs, you couldn't replace them. And another thing, we couldn't move our leads around, right? You understand that? The problem is though, is when we put these things upside down like this, gravity is going to try to pull them out. So that's why we don't allow you, every circuit you wire, if you can't figure out how to wire it with less than 2 plugs, everything jumps to everything else, right? You understand? It's just like when I go to the breaker on my house and I look at my breaker, there's only one wire coming into one side. I might have 15 plugs out there, but there's only one wire. Some people, when they get back in DC, they think if it goes to power, they have to run the dang thing all the way back to power. Could you imagine your house if you had 10 plugs and every one of them ran back to your breaker? They don't. All you see is one. Why? Because all the jumping is done what? Out in the circuit. The parallel is done out on the plugs. The plugs are designed. If you ever did any wire houses, one plug is designed to do what? To feed the next. They are designed to do that because that's where all our jumping goes. So we'll never see that. If you can't figure out how to do it, then that's something you need to start. And if you was an electrician, you got a business. You had to go out of business real fast if you had to run every plug back to the panel box, right? You understand that? You'd be using about 50 times more wire than what's required to wire the house. So these are called banana plugs. And we have a male, which is the rod, and we have a female, which is the rod. I know that might be kind of sexist, guys, but that's the name of the game. We have what we call male plugs and female plugs. So plugs have genders. So how many? Okay, like I said, I'll run this off. Not following procedures will deduct from the student's lab grade. Experiments will be performed in teams of no more than what? 2. All entries on lab forms must be made in what? Pencil. Y'all understand why, right? I got tired a long time ago trying to follow road maps of people wanting to use pens. Before starting a lab, this should be the same on both of them. What's the first thing you need to do?
Blank lab.
Yeah, the lab grade forms will have a folder for the class. It stays in the office like here. It's called motor control. And then when you open that up, you'll see a lab grade. Now, you should see this in that handout I gave you because every class that I teach requires lab grade.
It is.
And it's probably similar. The only thing that's changed is the title of the class. Okay, y'all understand that? So the first thing you're going to do is come up here and do what? Get one of these forms before you start a lab. Then what do you think you're going to do? You're going to fill in the top information on that form.
It says pencil too.
In pencil too. Everybody understand? Yes or no? Fill in the required information on the top of the form before starting the lab. Make sure to write your lab partner's name and first name. No more than one lab grade form at a time. That gets me too. I go back there and you have 15 lab forms and I'm trying to sign one and you're trying to dig and figure out which one is supposed to be. Next thing you're going to do is what?
So you can instruct the lab and.
For what?
Corrections and just.
So here we got this manual. Make sure I get this out. It's called Corrections in this book. I think it's going to be hard for y'all to find. In fact, it stays up here. So it's okay if you bring a chair up here and copy it down. And then, so we're not going to say, who's got the lab book? And then somebody's up here working on lab, not paying any attention to what anybody's saying anyway. And they got my lab book back there. And we're out there trying to find it. We're not going to have that problem. Why? So it's going to stay up here, right? You understand that? So the stapler's going to stay up here. The boxes that we put our labs in are going to stay up here. Everybody's going to stay up on this table. At the end of the class, I'll get everything and put it back in the office up here. Any problem? And you're going to document the changes in your manual. I don't care if your partner does it. You're going to document the changes in your manual. I don't have all these changes in my head, right? You understand that? So I'll come back there, and when I check your schematic, I'm going to check it according to your book. And if it pops in my head that you haven't made those changes, then we got a problem. We have people do that all the time. You know, if you see in here a big old thing that says skip, it means do what? If it don't say skip, it means what? Don't skip. I don't want to hear this. Well, they said we didn't have to do that. I heard that, I ain't telling how many times in my career. They said we didn't have to do it. When you ask them who they is, now if you say, Rich, you told us we didn't have to do it, then that's okay, right? But let's don't say they. That's almost as bad as using it. Write your name, write your first name, first and last name on the top of the experiment page. So what we do is that, first of all, the lab grade form, okay, that's going to be mine, right? You understand that? This is what I keep when I grade your lab. If you want your labs back at the end of the term, I'll give them back to you. The lab grade forms and the labs don't stay together. Y'all understand that? If you don't put your name on top of the lab grade form, then I don't know what lab goes with what grade. And plus, you're going to be stapling this little tiny form on top of another form. And what's the odds of somebody's getting this lab form tore off their lab? Well, if it gets tore off, then I no longer know what form goes with what's lab, right? You understand? And these are going to be stapled together, guys. We don't just stick them in here. I've had that happen too. People put 15 labs on there, and they just throw them in there, and the lab grade forms are not stapled, and they want me to figure out what goes where. Write your first and last name on the title page of the experiment. So every experiment has a title page, right? Now, the way the lab book is laid up, if you've got your lab book, you probably noticed we have a chapter title page, and then we've got a title page for each experiment. The chapter title page is not the title page for the experiment. It's the title page for the what? For the chapter. I don't care about the chapter title page. I don't care about the discussion inside the title, inside that section right there. Y'all understand that? So what are you going to do? You're going to turn in the title page for the experiment. Everybody understand that? Okay. Not having your lab grade form at the workstation filled in with the required information, add an instructor sign off will result in 10 points being deducted from the lab. Every lab is worth 100 points, by the way. So here I come back. We got 15. We got all these people in class. We got six groups in here. You're going to sign a thing up here saying that you need a sign off. I come trucking back to your lab table. You got 4 or 5 people sitting here waiting on me, and I come back there and you don't have your lab form. You said, "Oh, I don't have it," and you want to do what? You want to come back up here, get your lab form, fill it out, bring it back to me, and you should have had it what? Okay, y'all understand that? So now, not only are you mad at me, but all the other people that's waiting on me is what? Mad at me. Because I'm letting you have extra time to do something that you should have done to start off with. Any questions there? What does it say next? Even on your form, these should be the same. When your team needs a lab instructor check or help, one team member, not both team members, one of the team members will do what? Must write his or her name on the sign-off sheet located on the podium. Where's the podium at? In front of the classroom. So there's going to be a sign-off sheet up here. In the appropriate columns, write your name, place a checkbox if you need help or a sign-off, and write a number assigned to your trainer station. So what I do when I come up here is I don't write names down. I usually have a little slip of paper, and when you write your name on there, I write your station number. You notice up in the upper right-hand side of all these stations, there's a number. So when you come up here, you're going to write that number down. So when I got my sheet to make sure I'm doing it in the right order, that's all I do is I write numbers down. If you don't put your number up here, I don't know, I'm not going to write it up there for you, right? Y'all understand that? In fact, let me go ahead and, while I'm thinking about this. So how many people got here today? 1, 2, 3. I'm glad. Thank you. We got 10 people. This is a problem we have in this class. Is all my stuff is over in the other on the other building, and I gotta try to remember what stuff to bring over here. Lab procedures. See, it's even open up somewhere. This is going to be a little different than the one I gave y'all. It says, write the manufacturer number terminals. So when we wire up a circuit, and we'll talk a little bit more about this. When we wire up a circuit, what they have on the circuit, on the actual device itself, is they have what we refer to as manufacturer numbers. Now, the manufacturer numbers are put there by the manufacturer. These are unique to manufacturers, but they do have some standard sequences that we'll look at. Let's see if this will open back up. It's not, I'm in trouble. I think it's going to require me to restart my computer. But all these numbers on the top, who assigned these numbers? Can y'all see it? The manufacturer. So when we connect wires, we're going to do it by a ladder diagram. Well, before you connect that up, what you're going to do is you're going to go through your print and you're going to assign the manufacturer numbers to your circuit. And then that way, when you hook them up, you're not trying to go between manufacturer numbers and your line diagram, because all your numbers are on your what? On your line diagram. Y'all understand manufacturer numbers. So y'all document these on your ladder diagram before you start doing what? Connect them up. And plus it helps me. So when I come back there, I'm not going to try to figure out two different documents, right? I'm not going to try to figure out the manufacturer numbers, which are written on these terminals for you. By the way, they also put a schematic of what's going on up here in the upper right-hand corner. This is also up here on that, right? So you can actually see the actual schematic diagram of the device itself. So those are manufacturer numbers. Every part we have has manufacturer numbers on it. And that's the way you connect things. You connect things by the manufacturer numbers, right? Who puts those on there? Well, we wrote them on Lowe's, but they actually copied them from the manufacturer itself. So. Then it says, students in a team must take turns connecting circuits. Each team member must document the constructor of the circuit in the space provided on the lab grade form. The team member not connecting the circuit is a team supervisor and must provide manufacturer numbers as to where the connections are to be made. So y'all are a team, right? You understand? So I don't come back there and if a circuit's hooked up wrong, you can't say, well, Joe Blow hooked that up. I was out taking a break. That's not the way this works, right? You understand? You are a team. In fact, the one that's calling out the numbers is actually basically the supervisor, right? But you're both going to be graded. So if on the connection of the circuit, if everything's right, you are a team. So actually we got two eyes that's supposed to be looking this over, besides mine, right? Everybody okay? Check. Place a check mark. We got all kind of labs. When you look through your lab, you see there's little old tiny white boxes over on the left-hand side of each lab procedure. And you're going to be doing a lot of lab procedures that's going to require a lot of sign-offs. I'm not going to come back there and let you figure out what procedure step you're on, because why? So what are you going to do when you do these procedure steps?
Check them off.
You're going to check them off. Do y'all understand that? So that means when I come back there and you're ready for a sign-off, I know exactly which sign-off you're at. And I know what to ask you where you're at in the lab, right? Everybody understand that?
So,
Huh?
you talking about check marks going?
On your lab book.
Oh,
In your lab book. These are just procedures.
Okay.
Okay. So the experiment procedures. Beside each experiment procedure step, do what? Put a check mark after you do what? And ever have the instructor check your word procedure step. The instructor, it don't say maybe, it don't say might, it says what? Must initial your lab book indicating the steps have been successfully completed. Skipping over any instructor supervisor's checkoff will give you a 0 on that section of the experiment. Do y'all understand that? We have this happen all the time where people think, well, he's working on these guys, I'm going to go ahead and continue on, and then he can check me off when he gets ready. That don't work in this class. Because odds are you're fixing to do something that you're going to undo what I wanted to see, right? You understand? So when you hit the instructor sign off, what do you need to do? Go up here and put your name on that list, right? You understand? Don't put your name on the list and then go out and take a break. Because if I come up there and your name's on the list, I mark it off. If you're not in here, what am I going to do? I'm going to go to the next one. And when we talk about here, we mean both team members have to be here. So you're gonna put your name on the list, and I come back here, and John's gone somewhere to take a break or smoke a cigarette, and he says, oh, he'll be back in a minute. Go ahead and sign us off. I'm not gonna do that, because I ask questions. I do things when I come back there, right? You understand that? Huh? If your team member's not here, then this is covered in the lab book too. Let's get there too. All circuit checks must be made for short circuits. If we go back there and you did not check and it blows a fuse, you're gonna lose what? 20 points. I'll come back here and I'll perform a basic check, a safety check. The common side is L2. I'm gonna check L2. If L2 goes where it's supposed to go, then there is no short circuits in the system, right? Y'all understand that? When I do that, I'm gonna put a little initial out there, and then that means you can power the circuit up. It does not mean the circuit is checked up off. It means it's okay to do what? Power up. Most of y'all in my classes have been there before. That is not a check off. That is just so I'm not saying the circuit is working. I'm just saying it's okay to do what? Power it up. Who's supposed to know how the circuit works? Trainer modules that are not part of the currently connected circuit must be stored on the shelf below the lab table. All unused wiring jumpers must be hung on the bolt to the right side of the trainer. All unused wiring nuts must be screwed into a little bolt somewhere. Y'all understand that? Yes or no? Some of y'all do. Now this is what, so I don't want to come up here and see 15 modules up there, or people starting to wire up the next circuit. I hadn't signed this circuit off. So you got all these modules up there, you got all these wires running all over the place, right? You understand that? I understand that. And I'm coming there trying to do what? Check. This is what Kelton was asking. Student will not be awarded points for portions of an experiment completed by team members when they are absent or tardy. When the absent or tardy team member returns, he or she must continue labs at the point which the present team member is currently working. There is no time scheduled to make up labs in this class. So if you're absent, your team member is going to do what? Keep going. And then when you come back, this team member that was here is not going to let you make up that lab. I'm not going to let you do it. Okay, y'all understand that? Now, we scale the labs at the end of the semester. We scale it by 2 labs, which means if you mess out on 2 labs, you're okay. If you mess out on more than 2 labs, then you're messed up, which that's the way it should be, right? Y'all understand? There's no time in this class to make up labs.
That's fair.
Huh?
That's fair.
I know it's fair. I mean, you don't get paid if you don't show up for work, right? Unless you're the son of the boss. The son of the daughter, right? So if you're absent, and this happens all the time too, I'll be over here and the guy will be sitting over there. And I go over and I said, why are you over here? Well, he's making up that lab. He was absent. That's not the way this class works. If you're absent, then you just eat that lab. If you're absent a lot, then what should happen? I mean, if you're absent all the time at work, what are they going to do? Hopefully, unless you're the
Union.
huh? Even with union out of U.S. Steel, I think it was, if you miss like 5 days within a quarter, they get substitute measure, and the union won't fight for you if you don't do what? If you don't show up for work. So you say you got union, I remember that. Some of those guys got. I don't forgot what it was. It was like if you missed so many days within a quarter, they would give you 5 days off unpaid. And then after that, if you did it again within a year, they would terminate you.
Still have to come to work. It's in your record. It's in your record. You still got to come to work.
Yeah, they get 5 days off by schedule work.
They ain't gonna let you be punished and enjoy the time off.
Yeah, and I'm listening to it.
Okay, guys, lab grade forms are not to leave the classroom. All lab grade forms must be turned in to the instructor at the end of each lab. So students' projects can be verified. The lab grade forms will be returned at the end of each lab. It's up to you if you want to carry your labs home. A lot of guys will go ahead and staple their labs together. We got 2 boxes up here. One of them says labs ready to be graded. One of them says labs not ready to be graded. If you're not through, if you want to go ahead and staple it, but you don't want to take your lab, you think you're going to lose it, then do what? Put it in the not ready to be graded. If you don't put your lab forms, if you want to take your labs, don't take the lab forms home with you, because that is your official grade. Y'all understand that?
Have they got any lab books yet?
Yes.
Yeah, they've had lab books. The lab books wasn't the problem. The lab books was the textbook, and the textbook came in Monday, right?
I went down there, so last week they didn't have no, lab books for.
Oh yeah, they said they had plenty of those.
If
Huh?
for some reason you don't complete your lab, you can put it in the box and do it. when you-
Yeah, and by the way, we work up, I got a song that comes up, y'all learn it later on. And if you leave before that song comes up, then you'll be counted tardy in class, right? And usually it's 15 minutes before the class gets out when we're in lab. So it'll be about what? 1:15. Nobody else is working in this lab. Nobody else does anything. So there's really no thing that says I didn't have time. I've seen people leave 45 minutes and says, well, I didn't have time to start a lab. That's not true in this class, right? You understand that?
You don't have to finish it that day.
No, you don't have to finish it. But you can't say I didn't have time to start, right? You understand that? Because you're the only ones where you're assigned a station. All you need to make sure you do is just document where you're at. And that's why when you come up here and while you're doing it, you're checking off those marks, right? You understand that? And then when Jamie Grace sings, it's time to go. Y'all learn that song. Questions at the end of each experiment chapter. So, questions at the end of each experiment and the experiment chapter quizzes are not team efforts and must be answered individually by each student. Do not copy answers from any book or any other, or any students. Copying will do what? Result in a 0 score for all problems. So you're a team member for wiring, y'all team members for wiring circuits. Right? You understand that? You're not a team member for what? Answering questions. You understand that?
So you don't have to do the lab questions together.
No lab questions together. Everybody okay?
You don't want to put that part, no lab books one.
Don't answer no lab question together.
Yeah, you do labs, you wire circuits as a team, but the questions in the lab are your questions. They're not your team's questions, right? You understand that?
What's that, should have, answers should be about the same.
Well, they should be about the same, but they're not going to be the same. We taught, I know it's time to go start the test, but we did hexadecimal. In hexadecimal, you have numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you have A, B, C, D, E, and F. We had one of my students wrote a 6, and he wrote it like that. Then I had about 4 people that wrote down an uppercase G for a hexadecimal number. They wrote down an uppercase G as one of the numbers, and there's no such thing as a G in the hexadecimal. And you could tell the person they copied from. It was a smart guy in class. But these people, that's what you call copy. I mean, they didn't even what? They didn't even pay any attention to the questions. They just looked at this person's paper and copied. We're going to be giving the test down in room 200. Y'all know where room 200's at?